Hello everyone. This is the pre-lab lecture for crossed-aldol condensation. So that brings the point, first off, what is an aldol? Well, an aldol, an example here would be something like this, a structure like this. So you want to break down aldol, right? So first off, aldol is derived from the fact that something has an aldehyde functionality and an alcohol functionality. So aldehyde, alcohol, so aldol, right? So that just makes us an aldol. Now, one thing to point out here too, the aldols that we're seeing here, right? If you look with respect to where your carbonyl is, you have an alpha position and a beta position, and the alcohol is attached to the beta carbon. So that's something to keep in mind as we look at these reactions. Now, the other thing is this is called a crossed-aldol reaction. However, the reaction that you're going to do does not actually stop at the aldol. It actually goes to the condensation product, right, where you actually remove water from the molecule. So if this were to undergo condensation, you're going to take off or subtract, right, subtract water. And so what you would see in this scenario would be that, right? So you have the formation of an extra pi bond here, okay? And so we'll talk more in a minute why this reaction goes all the way to that condensation reaction. So first off, specifically pertaining to what you're going to be using, you're going to be using acetophenone. And so we are looking at acetophenone right there. And so the first real step in this process is that you're going to react that with a base. Okay, so in this case, this is a base, so it's going to have to react with an acid. And so in this structure, the most acidic part, or the most acidic hydrogens you have, are these right here, these alpha hydrogens. Okay, so we're going to see the base is going to take a hydrogen, and you're then going to get a negative charge on that alpha carbon. Right, and this is also resonance stabilized, so other reasons why we could see this happening. Right. Right, it is resonance stabilized as well. Now, but we're going to think about this as our product, specifically our enolate. Okay, so if you haven't talked about those in your lecture, these enolates, you're going to see them as primarily the real enolate form that to kind of explain what's going on here. You have an you think of enol, so it's like sort of like a deprotonated alcohol. So and then you have this double bond here. So ene right here, En, pertains to a carbon-carbon double bond. All alcohol, but it's all 8, so it's a deprotonated alcohol. All right, so that anyway, that's an enolate. Okay, and they are resonance stabilized. Now, once you have your enolate, that's when your next reagent will come in. And so we're gonna, let me look at my enolate here. I'll redraw it for you. Okay. And it's going to react with our aldehyde, this fellow right here. Now what's going to happen here, the enolate is going to act like a nucleophile, so it's going to nucleophilically attack our partial positive carbonyl carbon, and then we're going to see the pi bond being pushed up, and also you're going to have water here in your solution. Remember, you did create water up here, so you're going to have water here, so the oxygen the lone pair on the oxygen will take a hydrogen, and you are going to see right, so that's the carbon that was negatively charged, but we're forming a bond between it and the carbonyl carbon. So that's, I'm going to put a dot, I'm going to put a circle. So then that was our carbonyl carbon, and that oxygen now becomes an alcohol and the rest of the molecule. Alright, now this is the aldol form of the product. However, this is going to take one additional step. We're actually going to see what's called the condensation product of this. Alright, so I'm going to move this up a little. Alright, and so what we're going to see happening here, you have, if you notice that water did get deprotonated, so that's where my hydroxide came from. It being a base, it's going to react with something very acidic, and in this case, this alpha hydrogen is quite acidic, as similar to what we saw up here before, right? The hydrogen here, being an alpha hydrogen, it's very close in proximity to that carbonyl, so this is acting like an electron withdrawing group, deprotonating, or not deprotonating, but removing some of that electron density from the hydrogens there. And so the same process is going, right? It's happening again. We have our carbonyl, we have our alpha hydrogen, it will get deprotonated, and so the carbon-hydrogen bond here will break, donate between these two carbons, and then we'll kick off this OH group. So if you notice, we turn this hydroxide group into water, and then we kick off this hydroxide group. So it's kind of like a base catalyzed reaction, and so we will see the formation of a new pi bond to give us our condensation product. Now, one of the real driving forces here is this is actually more stable. This is thermodynamically more stable. Thermodynamically stable compared to the aldol. Because if you look here, you have two benzene rings, and you have all this double, single, double conjugation, right? So double, single, double, but then you get single, single, single to get to the next double. Well, if you notice, in kicking off this hydroxyl group and giving us the pi bond, you now have an uninterrupted, completely conjugated system, and so all that conjugation adds tons of stability. So anytime you have benzene rings being involved in your aldol reaction, you do want to check to see if by removing the alcohol, if you can get an uninterrupted conjugated system all the way through the molecule. So for instance, if you were to say look at a reaction of, let me move that so we can now see. If you were to look at this product, or sorry, this ketone here reacting with a base, you would still form the enolate at the by removing an alpha hydrogen. Right. And then if we took it a step further and looked at reacting it with another aldehyde or ketone, I'm just going to pick this guy here. I'm just going to draw something else, so don't fret. It's not really important for you to know all the ins and outs. But as we look here, we would see yet again that would attack the carbonyl carbon, push up the oxygen, and we had water, we formed water here, so that would get protonated. And so the product we would see here, or aldol product specifically that we would see here, so there's that carbon and then the carbonyl carbon, so that would become an OH, and then we would get our six-membered ring and our OCH3. Okay. Now at this point, this aldol would stop. It would not go to the condensation reaction because there's no conjugation to help drive it to that thermodynamically stable product. Okay, so this would stop here. All right, put a fork in it, it's done. Okay, now one other thing to kind of point out here, this is called a crossed-aldol condensation or crossed-aldol reaction because you have two different types of carbonyl compounds that react. So specifically here you have your acetophenone that becomes the enolate, and then it reacts with this benzaldehyde derivative as well. Now this is highly controllable. You're only going to see one enolate forming. This compound right here cannot form an enolate because it doesn't have any alpha hydrogens, and then also this can only form one type of enolate because this alpha carbon right here is the only one with hydrogens. That alpha carbon does not have hydrogens. So you only form one enolate, and from there it's going to react with the aldehyde. And this is the reaction of this enolate reacting with the aldehyde is a lot faster than, say, this reaction. So if we took the enolate and tried to react it with a neutral form of acetophenone, right, this attack is much slower than it is with the aldehyde. This methyl group here adds some steric bulk, so it's a lot harder for that negative charge to attack the carbonyl carbon compared to now you have a hydrogen there, so in essence that carbonyl carbon is wide open. So this really is the only product we would see in this reaction, this aldol that then eventually does turn into the thermodynamically stable condensed product. Okay, but since it is crossed, it is two different carbonyl compounds. This right here, if this were to keep going, this would be considered what's called a self-aldol reaction. You turned the acetophenone into the enolate, as shown here, the enolate, and then reacted with a neutral form of the other acetophenone. But like I said, this reaction is super slow. It's not going to happen compared to this. And so in essence, that kind of tells you, in order for this to favor these two different ketone, these two separate carbonyl compounds to react, all this kind of happens as kind of a one-pot synthesis. You have your acetophenone, your base, and your benzaldehyde derivative all in one pot reacting together, so that as soon as you make the enolate, it's reacting with the easiest carbonyl carbon, which would be the aldehyde. All right, so that is everything that we are looking at for the pre-lab here. At this point, you can start the quiz.